Today we're going to be talking about periodic trends. You should have done most of the reading for this beforehand, so I just want to go quickly through everything, or at least the important ones to us. So atomic radius, understanding how atomic radius works and the trends in atomic radius will help us build some of the other trends. So I'm going to start here, and they decrease. The atomic radius decreases going across a period, and that's because the electrons seem more positive charge in the nucleus. So let's take a look at let's do radius here. Let's take a look at the second period. Okay, so as we move across, we're always adding electrons into the second energy level, right? This is 2s1 all the way up to 2s2, 2p6. So we're always adding into the same energy level, which is roughly the same distance from the nucleus. Now, the problem here is that, or the interesting thing here, is that as we move across, the nuclei get larger and they have more positive charge because there are more protons there. So that increased positive charge in the nucleus means that each electron is going to experience a greater positive charge and be pulled tighter to the nucleus. Okay? And you'll see that trend all the way is always true. Okay? So that's atomic radius going across a period. Now, what about groups? It increases going down a group because you're adding more electrons. And as you add more electrons, you're adding them into higher energy levels, which are further from the nucleus. That should make sense. Electrons also don't really want to be near each other, so the more you add, the more you have to spread out. Okay, so your book has a couple like this, but I don't like the increases one way and decreases the other way. I like to just write them as always increasing. So we increase going this way, and we increase going this way. Okay. And that'll also be increase. All right, and kind of keep these pictures in mind. It really helps you understand what's going on. And I'll have one of these at the bottom of each page here. All right, now the next thing that I want to talk about are ions. So if we look at copper, here's copper. Now if I ask you for the electron configuration for copper, you should immediately realize that this has, this is one of the special cases. So I'm fine with a noble gas configuration here, so we'll start with argon. And then after argon, we're in the fourth period, so this is 4s2. Or you would expect it to be 4s2, but instead it's going to be 4s1. And then 3d10. Not argon 4s2, 3d9. Okay? And that's because things generally want filled outer subshells. Okay? Another way that a lot of elements go about this is by making ions. So rather than kind of shifting the electrons within, we can either get rid of an electron, in this case, or add an electron. And so when we form a positively charged ion, this is called a cation. An example of this would be something like Li plus or Mg2 plus. Okay, and here this is an anion, and an example of this would be like F minus or N3 minus? Ah. Okay, and there's a way, there are a couple ways that you can remember this. There's the one that I can't agree with. I can't really get behind. It's that cats are positive. I just can't agree with that. But, you know, cation, positive, cats are positive. It just doesn't stick with me because I don't like cats. But because I like to come up with my own little things here, I remember capo Annie, which doesn't mean anything at all. It's possibly the worst mnemonic ever. Capo Annie. But that actually sticks with me. Cations are positive, anions are negative. Boom. Whatever works for you. There's an important term here that you'll see a lot, and that's isoelectric, and that just means same number of electrons. So if sodium loses an electron, sodium atom has 11 electrons. So if it loses an electron, it's going to have 10 electrons, which is going to be isoelectric with neon atom, and we'll use that rather a lot. The next trend we're going to talk about is ionization energy. So you can take a neutral atom and add energy to that and knock loose an electron. And we saw this. This is an example of the photoelectric effect. Okay. Very similar. So this energy here that you have to put in to knock loose an electron is the ionization energy. And so I want you to pause, and I want you to look at your periodic table, and I want you to think about what atoms are readily want to give up their electrons. So remember, this is like energy that you have to put in to knock loose an electron. So what should have a really low ionization energy? Like what atoms just dying to give up an electron? If I look at the periodic table, something like, let's say, lithium. If lithium gives up an electron, it's going to be isoelectric or have the same number of electrons as helium, which is a noble gas. Remember, things are always trying to get to noble gas. So elements in group 1 should have very low ionization energies. Okay? Now, the important thing to keep in mind here is elements can have more than one ionization energy. Let's take an element like calcium. Okay, so here's my calcium element. I'm going to have to add energy, and that's going to make Ca plus E minus. Now the problem with that is Ca plus has 19 electrons, not 18, which is the closest noble gas, argon. So what's going to happen is this is going to happen again. Ca plus energy yields Ca2 plus E minus. Now we'd call this the first ionization energy, and this the second ionization energy. Okay, and you would expect the first ionization energy to be pretty high because that's not really great, and the second ionization energy to be a little bit, or to be lower in comparison to others. So let's go take a look at p-table again, and I'll put a link to this in the graphical organizer so you can kind of play around with it yourself. So here's ionization, okay, and here I can adjust whether I'm talking about first or second. So here we see lithium has a relatively low first ionization energy of 520.2 kilojoules per mole. And sodium is a little lower, potassium is a little lower, so we're looking for trends here. It looks like it increases as you go up, and then if you look across, it increases as you go across. Okay? There's one exception here, and that's going from nitrogen to oxygen. So we'll kind of talk about that in a minute. But let's take a look at second ionization energies now. So now, calcium has a relatively low second ionization energy, whereas something like lithium, not going to give up its second electron, right? That's really bad because you give up one electron and you're a noble gas, you give up a second electron, and now that's a disaster. I don't like that at all. So let's go take a look at the first ionization energies again, and let's talk about nitrogen to oxygen. So here's sort of these trends again. If I diagram the outermost subshell for nitrogen, okay, what I'm going to get is something that looks like this. It's got 3 electrons and the 2p subshell. 3 electrons are all going to look like this. So it's not all that happy giving up another electron, but if I look at oxygen, that now has 4 electrons in the 2p subshell. And if it gives up an electron, it's back to half filled, which is better than have it, or it's more stable than being partially filled, right? Like things like to be half filled or all the way filled. They don't like to be kind of mixies. So that kind of explains some of these blips on the trends. So again, increases as you go up and increase as you go across. The last thing that I want to talk about here is kind of rationalizing why these trends happen. So if I go back to p-table, for instance, why would it take more energy to remove an electron from lithium than from sodium? Well, lithium is smaller, the electrons are closer to the nucleus, so they feel more of the positive charge. So it's going to be harder to take them. Now, as you go across, okay, as you move across a period, why does ionization energy increase? It's for the same reason, right? There's an increase in positive charge, or it's for a different reason. There's an increase in positive charge in the nucleus, so each electron is being held a little tighter. Okay, that's the bottom line, and that's being able to explain the trend is important. All right, next trend that we're talking about is electron affinity. When an atom gains an electron, you form a negatively charged ion, which is called an anion, and you release a little bit of energy. Okay, so in your textbook, this energy is going to be given as a negative value. When we look at it on a moment in p-table, it's given as the positive value. So you just kind of have to be keeping these things straight in your head. Okay, so we're looking now at electron affinity. And as you can see, the trend here is a little bit more difficult to see, okay? In general, it looks like these elements over here have higher electron affinities than these elements over here. So why is it that fluorine would release a lot of energy when it gains an electron? Well, fluorine actually quite wants to gain an electron. So when it does that, it's going to become more stable, so it's going to release more energy, okay? And then as you move down a group, you can see that the numbers in general decrease, okay? Or, yeah, I mean, they don't change that much. But in general, they do decrease. And that's because you're adding electrons farther from the nucleus. They see less of the positive charge from the nucleus, so it's less of a gain, okay? So we increase across and decrease going down. So we increase up and increase across, okay? So that's electron affinity. Now, I want to take just a moment here to talk about ionic radii. So we did atomic radius. Now the weird thing here is that ionic radius is going to behave a little different. You just got to kind of keep these things in mind. And generally when I'm asking you these, I'm going to be asking you the ion versus the element. Okay? So let's take a look at calcium ion versus calcium element. So calcium ion has lost 2 electrons, which means that the remaining electrons, like there won't be as many remaining electrons, and electrons don't want to be near each other. They repel each other. So if you have fewer electrons, the electrons are actually able to get closer to the nucleus. So that means that a cation should be smaller. Cation should be smaller than the element itself. Okay? So an anion, so a fluoride ion versus fluorine atom gains an electron. Well, electrons don't want to be near each other, okay, so they're going to have to spread out a little bit. So you would expect the ion to be larger than the atom. And that's all I'm going to ask you for those. Okay? The last thing that we're going to talk about is electronegativity. Okay? So one of the things to keep in mind is that when we're talking about these ions, these elements don't really exist in isolation. Okay? They're not like single elements in a vacuum. You can do that, but that's not generally how it happens. Okay? In general, electrons will be lost by one atom and then maybe gained by another atom. Okay? And when that happens, you form a compound. Okay? And so the electrons that are available to be lost, gained, or shared in the formation of chemical compounds are referred to as valence electrons. Okay? And generally, these electrons are sort of the outermost subshell. Okay? So generally, when electrons are shared between atoms, a chemical bond forms. But not all atoms are very good at sharing the electrons. Often, the electrons end up being kind of concentrated around a single atom. So the kind of classic example of this is HF. Okay? If you were to look at where these 2 electrons are being shared on HF, they're basically sitting next to the the fluorine nucleus, because fluorine is actually not at all good at sharing. It's kind of a bully. And so we say that fluorine has a high electronegativity, or the ability of an element to attract electron to itself in a chemical bond. Okay? So this has kind of a weird scale, but in general it just increases going this way. And the thing that you really, really have to keep in mind here is the sort of, let's find p-table, let's find electronegativity, okay, increases as you reach the top right. So fluorine has the highest electronegativity. And this was sort of an arbitrary scale that was set out, and fluorine has a value of about 4. Okay, so it is the most electronegative. So the thing that you have to keep in mind is this sort of general increase up and to the right, and the 4 most electronegative atoms are, in order, fluorine, which is the most, oxygen, which is the next most, chlorine, and then nitrogen. Okay, and we'll use that next chapter.